Greetings, welcome to another edition. In this session, we'll be looking at algebra, the topic trigonometry. This session will be split into two. The first part will be covering trigonometric functions, and then the second part will be looking at trigonometric identities. So as a point of departure, what we are going to start looking at is what we call special triangles. And if you remember, we have two special triangles. So one is the 30, 60, 90, and the other one is the 45, 45, and 90 degrees. So let's have a look at this one. So this one is 1, 2, square root 3. That is the 30, 60 special triangle. And then the second one which we have is the 45, 45 degrees special triangle. So we have 45 degrees, another 45 degrees, we have 90 degrees, both sides are 1, then the hypotenuse will be square root of 2. So these are the two special triangles which will be of interest in this session. We will use them now and then and refer to them. So what I'm going to do is quickly write down the trigonometric ratios. So if you look carefully, sine of 30, if you remember, maybe just as a quick reminder, if you remember, sine of any angle is always the opposite side to that angle divided by the hypotenuse side to the angle. Then when we look at cos of theta, it is always given by the adjacent side. Very importantly, it is the adjacent sides relative to theta divided by the hypotenuse. And then for tan, it will always be the opposite side relative to theta divided by the adjacent side relative to theta. So let's go ahead and quickly work these out. So if you look carefully, sine of 30 degrees will just be equal to, if you look carefully, sine is given by opposite, so the angle is 30. So opposite to 30 is 1, and then the hypotenuse is 2. Done with that. Now let's have a look at sine of 60. If you look at sine, so we are at 60. What is the opposite side to 60? It is square root 3. And our hypotenuse is 2. Okay. Let's go now and have a look at sine of 45 degrees. If we go to the 45 degree mark, so lucky enough, both angles are 45, so we only need to do it once. What is opposite to 45 is 1. And then the hypotenuse, which is always the side opposite to 90 degrees, that will be square root of 2. Done with these. Now let's go and quickly work out what our cosines are. Let's have a look at cos of 30. So cos of 30 degrees, there's our 30 angle. Cos is adjacent, so what is adjacent to 30 degrees is square root 3. So that will be square root 3 over 2. And then let's do cos of 60. There's our 60 there. And what is adjacent to the 60 is the 1. So it will be 1 over 2. And then let's do cos of 45, which will be equal to the adjacent, my apologies, which is 1. So it will be 1 over the hypotenuse, which is square root of 2. That is how we get these. So now let's go and work out tan. So tan of 30 degrees, we are here, so it always opposite over the adjacent. So it will be 1 over square root 3. Then let's have a look at tan of 60 degrees. It should be very easy. We're at 60 degrees. What is opposite is square root 3. What is adjacent is 1. So this will end up being square root 3. And then let's go and do tan of 45. If you look carefully, tan is opposite divided by the adjacent, which will be 1 over 1. So the answer will be 1. Okay, so that is how we get our special triangle values. Others prefer writing this in a table form, but I'm not going to write it in a table form. I'm just going to leave it as it is. And then the next thing which I want us to focus on is converting from radians to degrees or from degrees to radians. So let's make a note of that. Converting from radians to degrees or from degrees to radians. So let's start by looking at converting from degrees to radians. So what I'm going to do is I'm going to have an angle theta, and this theta I'm going to call it's our angle in degrees, or let me call it the angle in radians. So how we move from degrees to radians is you take the theta, which is in degrees, and then you multiply it by pi over 180. That is how we convert from an angle which is in degrees to an angle which is in radians. So let's consider a couple of examples. Let's have a look at example 1. The angle theta which we are required to convert into radians is 90 degrees. So I'm going to use the formula above. So I can see that my theta is 90 degrees. And very importantly, by now I assume you probably know that that sign there at the top obviously stands for degrees. So if I now want to convert this into radians, what I'm going to do is I'm going to take my theta, exactly the formula which is above. So our angle in radians will be our angle in degrees multiplied by pi over 180. So this means that our theta, when it is now in radians, it will simply be 90 multiplied by pi over 180. And if you look carefully, this is just the same as pi multiplied by 90 divided by 180. And this just gives you 1 over 2. So our answer ends up being pi over 2. So this means that when we look at angles, 90 degrees is actually equivalent to pi over 2 radians. Very important. Okay, so let's have a look at example 2. For example 2, we are still required to convert the angle theta from degrees to radians. And now what we are given is an angle of 60 degrees. So what we are going to do is we are going to use our formula, the blue one, to be able to calculate what this will be. So our theta in radians will simply be our angle in degrees, which is 60. Then we need to multiply by pi over 180. And you should come to a realization that 60 divided by 180 gives us 1 over 3. So this becomes pi over 3. So meaning any angle which is 60 degrees, if we want to use radians, we are going to just use pi over 3. So let's go to the next page to example 3, where we are supposed to convert an angle theta of 30 degrees. Okay, let's have a look at example 3, where we are still required to convert the angle theta from degrees to radians. And what we are given is an angle theta is equal to 30 degrees. We'll use our formula where we have our angle in radians. It will always be given by our angle in degrees, which is 30 in this case, multiplied by pi, divided by 180. And this 30 over 180, it should give you 1 over 6, which means our answer is pi over 6. What this means is that our 30 degrees is equivalent to pi over 6 radians. So whenever we find ourselves in a point where we are supposed to use radians, it should be easy for us to do the conversion. Let's look at example number 4. Example 4 still requires us to convert our angle, in this case it is 45 degrees, to radians. Our formula does not change. Our angle in radians, you should be getting a hang of it, will just be 45 multiplied by pi over 180. And this 45 over 180, it goes 4 times, so it will be 1 over 4. This gives us just pi over 4. So this means when you are working with trigonometry, wherever you see 45 degrees, this is equivalent to pi over 4 radians. And some of you might have seen their calculator has a rad function. So that rad stands for radians. So what we are now then going to do is to quickly look at our triangles, our special triangles which we drew earlier, and see with our knowledge now how we can transform them from degrees to radians. So if you look at what we have, the side, this triangle is written in terms of degrees, and what we want to do on the other side is to write it in terms of radians. So I'll just copy that, and then we just go and replace the angles. So you should be in a position now to easily find these angles. So where there was 30, you should realize that that angle is the same as pi over 6. Where there was a 60, that is pi over 3. That is how our special triangle becomes now. So we have our special triangle. So when we convert to degrees, or from degrees to radians, it becomes that. So we'll also consider the second special triangle which we drew, the 45 one. We'll just quickly write it in terms of degrees, which we did initially. Then all what we'll do now is just write it in terms of radians. So let's paste it there. And we know how to convert the 45 and the 45 to radians. So you can easily go and do so by simply multiplying them by pi over 180. So we have pi over 4 and we have pi over 4. So these are our special triangles when we convert from using one unit of the angle, which is degrees, to another one, which is radians. The next thing which we'll be looking at will be the cast diagram. So some of you should remember this, but if you don't remember it, it's okay. I will remind you. So there's something which we call the cast diagram, where the C stands for your cosine, and the A stands for all, and then the S stands for sine, and then the T stands for tan, which is called tangent. Okay, so how the cast diagram is it tells us in which quadrants is sine, cos, and tan, are they positive and negative. So let's focus on that. But the diagram which we are going to do is we are going to look at a diagram which is in degrees. So this diagram, which I'm going to draw here, is in degrees. And then we'll draw one which is also in radians. So let's quickly draw it. There we go. Here's our cast diagram. And what you need to come to an appreciation is the quadrants. So this is the first quadrant. And then we have the second quadrant. The third quadrant. And then lastly, we have the fourth quadrant. And what is very important is to understand where are the trig ratios all positive. So on the first quadrant, all of these trig ratios are positive. So the A here stands for all, as I mentioned above. And then on the fourth quadrant, it is only cos which is positive. And then on the second quadrant, it is only sine which is positive. And on the third quadrant, it is only tan which is positive. That is how we end up getting our cast. Our cast diagram. So it just tells us what is positive on which quadrant. So quadrant 1, any angle which is on quadrant 1, when you take sine or cos or tan of that angle, you'll get a positive number. So what are the angles which describe the first quadrant? Remember, we're still working in degrees. So the angle which is this side is 0 degrees, just above here. And here the angle which we have is 360 degrees. At the top there, the angle which we have is 90 degrees. This side, the angle we have is 180 degrees. From the other side, it's minus 180 degrees. And then the angle which we have here is 270 degrees. Maybe let me leave the minus 180 degrees for now. Okay. These are how our angles are. So whenever we see an angle, we need to be able to map it to a specific quadrant. So whenever we see an angle 90 minus theta, we should think of the first quadrant. Whenever we see an angle 90 plus theta, we should know that we are going to the second quadrant. And when we see an angle 180 minus theta, we should know that we are also speaking of the second quadrant. This is very important for you to remember. And when we're speaking of the third quadrant, whenever we see an angle 180 plus theta, you should by default know that we are speaking of the second quadrant. Others, you would use 270 minus theta, but I prefer not that. And when we see an angle 360 minus theta, you should know that we are speaking of the fourth quadrant. Then also on the first quadrant, we also have an angle of 360 plus. So these are the most important angles which will help you to identify the quadrants. This is our cast diagram in degrees. So what we'll do is we'll quickly copy our cast diagram and quickly write it in radians, because now you know how to convert from degrees to radians. So we'll start on the first quadrant. So we have 90 minus theta. So when you convert 90 degrees to radians, you will get 90 multiplied by pi over 180. That will give you pi over 2. So once we see pi over 2 minus theta, you should know that we're speaking of the first quadrant. Okay, so let's deal with this one. So here we have 360 plus the angle theta. So when you convert 360 into radians, you just take 360 multiplied by pi over 180. That will give you 2 pi. So meaning whenever you see 2 pi plus theta, you think of the first quadrant. Then we convert the 360 on the third quadrant into radians. When you convert 360, you'll say 360 multiplied by pi over 180. That will give us 2 pi. So meaning wherever we see 360, when you convert it to radians, what you get is 2 pi. So that angle will be 0 there. And then here we'll end up with 2 pi. And then the 90, we've had a chat. Convert 90 to radians, it becomes pi over 2. Then when you convert 180 degrees to radians, you'll just have 180 multiplied by pi over 180. That will actually give us pi. So it means wherever you see pi minus theta, you should know we're speaking of the second quadrant. And when you see pi plus theta, we're speaking of the third quadrant. Then let's quickly replace that 90 there with just pi over 2, and then we need to replace the 270, which will just be 3 pi over 2. And then the 180 that is sitting there, it will just end up being pi. So we are gonna have pi like that. That is how we convert now our diagram not to be in degrees, but our cast diagram to be in radians. Okay, this is very important for you to make sure that you do understand, because we build up on it. Something which is worthy of noting before we depart here is that this 2 pi plus theta here is a full revolution. And you'll see what I mean shortly. So let's go to the next page and quickly worry about some standard identities which you need to be aware of. Or let me call them standard properties that you need to be aware of. So the first thing is that when you have cos of pi plus theta, what you need to realize is that the pi plus theta means that you're on the second quadrant. And by now, looking at the cast diagram, you should know that only sign is positive there. So this becomes negative cos of theta, because cos is negative. And then when we have sine of pi, my apologies, this is actually the third quadrant, it's plus. So let's fix that. That is the third quadrant, not second. So let's quickly deal with the sine one. So if we have sine of pi plus theta, you should look carefully and realize that this is still the third quadrant. And on the third quadrant, sine is negative. So I'll get negative sine of whatever the angle is, which I'm adding to the pi. And then when we get to tan of pi plus theta, I need to remember that here we are in the third quadrant, very importantly. And what you need to remember is that your tan is positive because you have your cast looking like this, CA. cast, C-A-T. And this here is quadrant 3, that there. So our tan is positive. So this means our answer will be positive tan of whatever we are adding to the pi. And then we can go to sine of pi minus theta. Pi minus theta, you should now know that this is the same as 180 degrees minus theta. So the same way you are able to find your angle in degrees is the same way you should be able to think of your angle in radians. Okay, so this here, as we can see, it is the second quadrant. And according to our cast diagram, on the second quadrant, which we see by having an angle of pi minus theta, our sign is positive. So we are just going to go there and equate this to positive sine of theta. Then we go and do the same with cos of pi minus theta, which it is in the second quadrant and only sine is positive. That's what the S is for. So this means everything else is negative. So you'll have negative cos of theta. Then we can go to our tan. Tan of pi minus theta. Tan is in the second quadrant here because of that angle and it is negative. Only sine is positive there. Okay, that's it. So now what we need to go and do also is to have a look at sine of 2 pi minus theta. So the first thing we need to realize is that here we are on the fourth quadrant. And on the fourth quadrant, it's only cos which is positive. So which means sine and tan will be negative. So here I need to say negative sine of the angle I'm adding or subtracting to 2 pi. And then if I have cos of 2 pi minus theta, this will be negative. So we said it's only cos, so cos will be positive. Then if we go to tan, this will be negative tan of theta. That is what we get on the fourth quadrant. And then we can go and worry about when we have a complete revolution. So when we have cos of 2 pi plus theta, essentially this just goes back more like to the same point. So that there, it goes back to the same point as theta. So whenever you have a 360 plus, because sine is, it has a period, or because cos has a period of 2 pi, this will just be cos of pi, like this. And then when we have sine, it will be 2 pi plus theta, which will give us sine of theta. Okay. And then cosine, because it will have 2 periods, it will amount to the same thing. So if we take tan, and then we do 2 pi plus theta, it will end up being tan of theta. Okay, that is what we get. And then we can now worry about something which we call co-ratios before we depart as part of our identities. So co-ratios are more, centered around 90 degrees. So they're more centered around 90 degrees, or in radians, that would be 2 over pi radians. So what is going on there? Well, if we find ourselves with the cos of 90 degrees minus theta, which is the same as cos of pi over 2 minus theta. this will always, when you have a 90 minus, it will always switch to a sine. So if you have a sine, you switch to a cos. If you have a cos, you switch to a sine. So this will end up being sine of theta, which means if we have sine of 90 degrees minus theta, which is in the first quadrant, this is the same as in radians, pi over 2 minus theta. Because I said when we're dealing with co-ratios, you change from a sine to a cos or from a cos to a sine, this will just become cos of theta. So what is the important note here? What is important is that we switch from a sine to a cos, or rather we switch between cos and sine. That is what we do with co-ratios. Once you see a 90 or a pi over 2, you need to figure out what is the current trig ratio and what am I switching to. So it's either you switch from a cos to a sine to a cos. So this is the case when you have 90 minus. But when we have 90 plus, 90 degrees plus theta, which is just the same as pi over 2 plus theta. What is very important to note is that this here is on the second quadrant. So the dynamics, they change slightly. So you need to make sure that you are careful when you are working with such. So let's see what I mean. So if we have sine of 90 degrees plus theta, what we need to look at is, this is the second quadrant, obviously, as I noted on our cast diagram. Let's quickly jump back to it. There you go. So 90 plus is on the second quadrant. So we need to figure out this one, which is here, the trig ratio. Is it positive or is it negative on the second quadrant? And by now you should know sine is positive. Then because we said with trig ratios, we switch to either sine or cos to sine, then I'm just going to put cos of theta here. But very importantly, this sine here was determined by the trig ratio, which we saw there. Sine in the second quadrant, is it positive or negative? It's positive. We put the positive, you switch to a cos. Okay, let's make some space and quickly write down, or maybe let's go to the next page. Let's have a look at cos of 90 degrees plus theta, which you can easily write in radians. We need to look at what is going on this side. So we have established already that this here is the second quadrant. But now what we need to ask ourselves is, the trig ratio which we see there, is it negative or positive on the second quadrant? And guess what? Cos is negative. And because we are dealing with trig ratios, we need to switch to a sine. So you'll just have negative sine of theta. These are very important for you to make sure that you understand and you do get them right. Okay, let's go and have a look at two more cases here. So when we have cos of negative theta, the answer is always the same as positive cos of theta. I'll let this slide. When we have sine of negative theta, the answer is always the same as negative sine of theta. And then when we have tan of negative theta, the answer is always negative tan of theta. Okay, these are very important for you to make sure that you understand all of these. If you understand them, you are good and set to understand trigonometry. Now let's jump to another topic where we will be looking at trigonometric identities. And let's see which are the identities which we need to make sure that we understand. The first trig identity which we need to make sure that we know, which is fundamental to trigonometry, is cos squared theta plus sine squared theta. This will always give you 1. And you can form different, variations of this. You can easily write sine squared theta as 1 minus cos squared theta. Someone else can choose to write cos squared theta as 1 minus sine squared theta. This is fundamental. Another trig identity which we want to be looking at is that 1 plus tan squared theta will give us sec squared theta. Very important. Another one, which all of these we can easily derive and show why they amount to that. Another one is cot squared theta plus 1 equaling cosec squared theta. Okay, just write cosec. That is what cot squared plus 1 is equal to. Something fundamental which you should also remember is something which we're calling under trigonometric identities. You are calling them compound angles. So what are these compound angles identities? Well, the first one is that if you have sine of A plus B, this is the same as sine of A cos of B, and then plus sine of B cos of A. And then if we put in a minus, you'll have A minus B equals sine of A cos of B. The minus comes in between. Then you have sine of B multiplied by cos of A. These are for sine. And then let's have a look at what is going on for cos. So if we have cos of A plus B, what is going to happen is this will be equal to cos of A cos of B minus sine of A sine of B. What is very important to take note of, which you can easily forget, is the signs. So when it's a plus inside, it becomes a minus outside. Let's look at when we have a minus inside now. So if you have A minus B, this will be cos of A cos of B. I'm sure you could guess it. It will be a plus. Sine of A plus multiplied by sine of B. It's very important that you take note of those signs because they do change. Okay. Now another aspect which we need to look at as part of our identities is what you call the double angle formula. Let's call them double angle identities. So how do we deal with these? Well, if you find yourself in a position where you have sine is equal to 2a, this can be written as 2 sine A cos of A. So what is very important is that the angle is no longer double now, but we have a sine and a cos multiplying one another, and then we put in the 2 at the front. That is the double angle identity for sine. What about cos? For cos, if we have cos of 2a, we have a couple of them. So the first one, you can write it as cos squared a minus sine squared of a. That is the first one. So this here, I'm going to write it more like this. So that's the first one. And then the second one, you can write this as, maybe let me just write them as separate lines. So your cos of 2a can also be written as 2 cos square of a minus 1. What is very important, the angle is no longer double. Okay. Or our cos of 2a can be written as 1 minus 2 sine squared a. These are the double angle identities which you must make sure that you do know of. Very important. So let's look at other useful trig identities which will be very useful when we start answering questions. So let's note them down as other useful trig identities. What are those? So the first one is going to be sine of a. So there's a couple of them. When you have sine of a multiplied by cos of b. These can be splitted and be made a sum by simply having half of. The derivation, in fact, for this is extremely easy, but that is not the focus of our session. Then plus sine of a minus b, close and close. This is the first one, very important for you to make sure that you do know. Then the second one, we have sine multiplied by sine. So sine of a multiplied by sine of b. So if you find yourself in such a case, how else can you write this? And the answer to that is half of, open bracket, you have cos of a minus b, then minus cos of a plus b. Okay, that is how you deal with that one. Then let's see when we multiply a cos and a cos. So when we have cos of a multiplied by cos of b, you can use all the standard, trig identities which we have above to be able to derive these formulas. So this one will be half of cos of a plus b plus cos of a minus b. So that product can be made the sum. Very important. Then we have others also, which we need to make sure that we know, where instead of having a product of two trig ratios, we either have the sum or the difference. So if I have sine of c plus sine of d, how else can I simplify or write this in a compact way? And this just becomes 2 into, so I'll need to make some space. It becomes 2 multiplied by sine of, you will have half of the angle c plus d, and then multiplied by sine of half the angle, sorry, this is cos half the angle of c minus d, like that. And then we have another one where we have a minus instead of a plus in between. So let's say we have sine c minus sine d. What is this equal to? This will be 2 cos of half the angle c plus d and then multiplied by sine of half the angle C minus D. Okay. Then we have another one, which is going to be when we have coses adding on each other. So let's say we have a cos of C plus a cos of D. This will be 2 multiplied by cos of a half into C plus D. Let's try that again. And then multiplied by a cos of a half C minus D as the angle. Then let's put up the last one, which is when you have minuses. So when you have cos of C minus cos of D, this will be equal to minus 2 sine of half of the angle C plus D, and then sine of half the angle C minus D. Let's try and squeeze that in, C minus D, like that. So these are the other useful identities which you need to make sure that you are aware of. There's one last one which you need to make sure that you are aware of. Maybe I'll do it as we do questions. Let's let that one pass. Okay, so let's dive into questions time. So for the questions which we'll be looking at, it will be questions which are combining all the concepts which we have learned so far. And with all of those concepts, we want to assess how comfortable are we with answering the questions which we are going to be looking at. So we'll start with the first question, which will carry on from the last example. So this will be example number 5. So what we want to do is we want to express sine squared theta in terms of cos 2 theta. So what does this question mean? Express sine squared theta in terms of sine squared theta in terms of cos 2 theta. So what this means is that this here must be our subject, because that is what we want to express. We want to express sine squared theta in terms of what? In terms of cos 2 theta. But what we then immediately remember is that previously we did this here. This looks like a double angle. And they say that we need to express it in terms of sine squared theta. So how do we do that? Well, since we are dealing with a double angle, we'll write what we know about the double angle. So cos of 2 theta, if you refer to the double angle identities here, we wrote it. It is equal to 3 expressions. But because I can see that they are saying we should express sine squared theta, so it means I should choose a form where I can make sine squared theta to be the subject. So it means I need to choose the form which is 1 minus 2 sine squared theta, like that. Then what I do is I start doing my transposing. So I can transpose that to that side and this to that side. So if you look carefully at what happens, we have 2 sine squared theta. This will be equal to 1 minus cos of 2 theta. So we can see that we headed in the right direction, because we are somehow now writing sine squared theta in terms of cos 2 theta. So we know for sure, because we are trying to make sine squared theta the subject, we need to remove that 2 by dividing by 2 both sides, and there's nice cancellation of terms. So what does this mean? This gives us that our sine squared theta will be equal to, I'll put the half and then put everything inside the bracket. It will be half of 1 minus cos of 2 theta, like this. That is what we get when we make sine squared theta the subject using the double angle identity. Okay, let's go and have a look at example number 5, where we will be making cos squared theta the subject, or writing it in terms of cos 2 theta. Let's now have a look at example number 6, where we are told to express cos squared theta in terms of cos of 2 theta. As always, we have come to an understanding that cos squared theta is the subject, and that cos 2 theta is somewhat a double angle, so we need to express the subject in terms of cos 2 theta. I then remember my double angle expressions, that I can have a cos double the angle. I can write it in terms of sine, or in terms of cos, or in terms of cos and sine. So if I look at my problem, they want me to express now cos squared theta, which means I need to take the second form here. So I'm going to go and quickly write down my double angle expression to theta, which will have what we need. So it is 2 cos squared theta minus 1. Okay, then we can now carry on and make the 2 cos squared theta the subject. So I can have 2 cos squared theta equals, if you look carefully, it will be cos of 2 theta plus 1. So we can transpose this the other side, but remember, you can always move things around and write one side on another one. But what we want is the cos squared theta, not the 2 cos squared theta. So we need to go and divide by 2, like that. And don't make the mistake that these cancel. They do not. That is the angle. So if we finalize our answer, you will see that our cos squared theta will just be half of 1 plus cos of 2 theta. That is what we get as our answer for example number 6. Okay, so let's have a look at example 7. Example 7 reads, find an expression for sine theta to the power of 4 in terms of, the power is all, in terms of cos multiples of theta. So essentially, if I can paraphrase these, is that we don't want powers on the cos. So meaning we don't want to see a squared or a cubed. We should simplify this sine theta all to the power of 4 until it's written just in terms of cos and angles, where there's no power at the top of the trig ratio. So we have a couple of options, to go about dealing with this problem. So as you can see, we have sine to the power of 4, which we can write as sine squared theta multiplied by sine squared theta. And what we know is, because our question leads us that we should somehow write these in terms of cos, we know that this and this can be written in terms of cos. So these, they can be written in terms of cos. And we don't want to, for example, write this as 1 minus cos squared, because it defeats the purpose. It's just taking us around and around, and we made it clear that we want to eliminate the powers. So I'm not going to go there and replace this with, for example, replace it with 1 minus cos squared theta. That is not a good move. This here is not smart. at all because the power will not disappear. So rather we'll use what we learned on example 5. So if you look carefully, from example 5, we know something. From example 5, we're able to derive that whenever you have cos squared of theta, you can write this as 1 over 2 multiplied by 1 minus cos of 2 theta. So there's no angle and no double anything there. So this means that what we have there, we can write it as 1 over 2, 1 minus cos of 2 theta, then multiplied by 1 over 2, 1 minus cos of 2 theta. This here, that's what we can do. And then now all what we can do is to go ahead and start multiplying. So if you look carefully, I will have 1 over 4 into 1 minus cos of 2 theta multiplied by 1 minus cos of 2 theta. So if we quickly do some foiling there, you will see that we'll have 1 minus 2 cos of 2 theta, and then plus, we'll end up with the cos squared 2 theta. Okay, this is what we have. And then now, this becomes a problem, that power there. Because they said multiple of cos thetas, not that we should be multiplying the cos thetas. So the power we do not want. That is a problem there. So how do we go and deal with that problem? Well, if you look carefully, you will see that we want to write that cos squared 2 theta. How do we deal with it? When I look at example 6, it helps me in part. So let's remember what we did. So I want you to remember example 6. So what did we end up finding on example 6? It was that cos squared theta is 1 over 2 into 1 plus cos of double the angle. So what is very important to take away is that that angle which is there and that one, that is double the angle. And that removes the square. So what does it mean? It means that this cos squared of 2 theta here will actually be 1 over 2 into 1 plus cos of. Now I need to double this angle. As we did with the other one, double the angle. And when you double the angle, it is 2 theta. It means what we get is 4 theta. So it means that cos squared 2 theta, I can now go ahead and replace it with this expression. And if I can rewrite it again, it will simply be 1 over 2 plus 1 over 2 cos of 4 theta. So this means that if I go and replace it there, our sine 4 theta will be 1 over 4 into 1 minus 2 cos of 2 theta, like that, then plus a half, then plus a half cos of, let's make some space. This was a very nice but easy problem which incorporates what we were doing. 4 theta, close the bracket like that. So essentially our final answer just becomes, if you look carefully, that plus that will give us a 3 over 2, and then multiplied by the 1 over 4, that will give us a 3 over 8, I believe. And then the others will just remain as they are, minus 1 over 2 cos of 2 theta, and then plus, this will be 1 over 8, and then cos of 4 theta. So that is what we are going to have as our answer when we want to express sine theta all to the power of 4 in terms of multiples of cosine. If they were saying multiples of sine, we're going to take a slightly different approach. Okay, but let's keep it here and move on. Okay, so let's have a look at example 8. So on example 8, we are required to find tan of theta if we are given 9 sine square of theta minus cos square of theta, and all of that equals 7. As a hint, we are given that we should divide by cos square of theta. But before we do the revision, I want you to remember something which is very important but fundamental, which is that 1 divided by cos theta will give us sec theta, which means whenever you have a division by cos squared theta, you will end up finding sec squared theta. And also, I need you to remember that sec squared theta will always be equal to 1 plus tan squared theta. And we are trying to solve for tan theta here. So what we are going to do is we are going to take the expression as given on the hint, go and divide by cos of squared theta all over. So cos squared theta, what you do on the left, you do on the right. So if you look at what will happen is sine over cos will obviously give us tan. So we'll have 9 tan squared theta. This will be minus 1 equals 7 sec squared theta. Because the cos is on the denominator, it becomes a sec when it goes up. But now we need to use even that identity because we are trying to solve for tan. So we don't want the sec to be there. So we want everything to be in terms of tan so that we can make it the subject. And that sec there, we know it is 1 plus tan squared theta, like that. So this becomes 9 tan squared theta minus 1 equals 7 plus 7 tan squared theta. Then I can just do some transposing and wrap up this problem. So this should go that side and this should come the other side. So what we end up having is 9. So we end up having 9 tan squared theta minus 7 tan squared theta, and this is equal to 7 plus 1. And this will give us a 2 tan squared theta equals 8. And obviously, because our question was asking us to find tan theta, so we need to divide by 2. Then we'll take the square root afterwards. So let's go ahead and divide by 2. What you do on the left, you do on the right. So that what we end up having is tan theta squared will be equal to 4. And all what is left now is we need to remove that. And for us to remove that, we need to take the square root. And what you do on the left, you also do on the right. So if we put in a square root of, or alternatively, we can even do a difference of 2 squares. So if you look carefully, we can have tan squared theta minus 4 equals 0. And this will end up being tan theta minus 2. And then tan theta plus 2. It's a difference of 2 squares equals 0. So your tan theta can be 2, or your tan theta can be -2. Okay. This is what we find as our answer for tan theta. This concludes example number 8. Okay, let's have a look at example 9. So example 9 looks similar to an example we did, example 7. The only difference is for example 7 we had a sine, and for example 9 what we have is a cos there. So we want to express that cos theta all to the power 4 in terms of cos multiples of theta. So the first thing which we want to note off is that we don't want powers on the cos. Okay, so let's go ahead and deal with this problem. So the first thing we are going to do is split this up into chunks which are digestible, if I can use the term. Why is this important? This here we covered previously when we were doing some identities. We saw that this is the same as cos squared theta is the same as 1 plus cos of 2 theta, like that. You can express it this way. So by doing that, we would have eliminated the squares already. Then we'll go and worry about foiling. So we have a half into 1 plus cos of 2 theta multiplied by a half, 1 plus cos of 2 theta multiplied by a half. So if you look carefully, this will end up in 1 over 4. Then we have 1 plus cos of 2 theta multiplying 1 plus cos of 2 theta. So all what we do now is some foiling. And when you do so, you will see that you get 1 plus cos of, or 1 plus 2 cos of 2 theta, then plus cos squared 2 theta. And this here is the problem. Why is it a problem? It is a problem because we have a power. And as we said, we don't want powers on the cos. So we need to deal with this. However, we already know the blue expression here. So if you look at the relationship, which I noted previously, we can just zoom in again. If you look at the angle which is there and the angle which is there, the relationship is that they are double. So we double when we are going in that direction. Now we have cos squared of 2 theta. So if we want to simplify it such that there's no longer the problem of the square, it will be 1 plus cos of, we should double the angle that was here to what is going to come there. So we double the angle. That is what we can see as a trend from the formula. So when we double that 2 theta, it becomes 4 theta. Very important. Then we can now quickly do some foiling, and then you'll see that we'll have a half plus a half cos of 4 theta. So with now this, we can go and sub it back and then start doing our work. So when we go and sub it back, you will see that we'll get 1 over 4 into 1 plus 2 cos of 2 theta plus a half cos of 4 theta. So when we multiply and conclude this answer, you will see that what we will end up having will be 1 plus a half, which will be 3 over 2, multiplied by 1 over 4, that will be 3 over 8. And then plus 1 over 2 cos of 2 theta then plus 1 over 8 cos of 4 theta. That is what we get when we find the expression for cos theta all to the power 4 in terms of cos multiples of theta. I hope it makes sense. Let us have a look at the next example. Okay, so let's have a look at example 10. So for example 10, we are required to prove that cos of 3 theta equals what you can see. And as a hint, we are told that our 3 theta is 2 theta plus theta. And the reason why we are given this hint is that we are used to double angles and single angles. So 3 looks better and we can better work with it when we express it in terms of angles we are used to, which in this case it's a double and a single angle. So what we are going to use here is the idea of cos of A plus B, which we covered earlier. This is cos of A, cos of B, then minus sine of A, and then sine of B. So let's go ahead and deal with this. So our cos of 3 theta will be cos of 2 theta plus theta, which will be cos of 2 theta multiplied by cos theta minus sine of 2 theta multiplied by sine of theta. Very importantly, if we look at our expression, it is in terms of cos. On the right hand side. So this means that here, it means when I look at my double angle expression, I'm going to look at the one which is written in terms of cos. So essentially cos 2 theta is equal to cos squared theta minus 1. This double angle expression you should be familiar with now. And then for the sine, we also have a double angle, and unfortunately, it really doesn't change. It is just 2 sine theta cos theta. Okay, so let's go and plug back. So if you look carefully, for the cos 2 theta stuff, we're going to have cos squared theta minus 1 multiplied by cos of theta. And this is going to minus, if you look carefully, we have sine of 2 theta, which will be 2 sine theta cos theta, and this is multiplying sine theta. So if you look at what happens when you do some foiling of that, what we will end up getting is 2 cos cubed theta minus cos theta. Then when we multiply the other one, you get minus 2 sine squared theta multiplied by cos of theta. So we're getting there, but now the issue is that we now have a sine squared theta. But when we look at our answer, it is in terms of cos theta. So what you should remember, something we learned earlier, is that sine squared theta can be written as 1 minus cos squared theta. Very important. That's why we had to cover those basics. So this will be equal to 2 cos cubed theta minus cos theta minus 2 into 1 minus cos squared theta multiplied by cos theta. So I can start doing my foiling and see what we obtain. So when we do our foiling, you'll see that we'll get minus 2 cos theta, then plus 2 cos cubed theta. And guess what? We have like terms. So this, the blues are like terms, and the golds are also like terms. So we should add those so that you will see that our answer, cos of 3 theta. When you add the blues, it's a 2 by 2 that becomes 4 cos cubed theta minus the golds. It is 3 cos of theta. And that is exactly what they wanted us to show. So it is very important that you get comfortable with using the trig ratios in different ways, be able to manipulate them until you get the desired answer. Okay, so let's have a look at example 11. So we are required to use the double angle identities to prove the identities below. So the first one is sine of 2a equals 2 tan of a divided by 1 plus tan squared of a. Something which is important, which I need us to remember as we go about answering this question, is that 1 plus tan squared theta, this is always equal to sec squared theta. And one important thing also that we need to remember is that 1 divided by cos, or not cos, but rather sec squared theta, this just becomes cos squared theta. Why is this important to put down ahead? It is because this is going to be useful in our answering of this question. So make sure that you always at all times try and link what you learn with what you will do, as you go forward. So that there is just the same as sec squared theta. And I just mentioned to you that when the sec is on the denominator, it always just comes up as a cos. So what we have, rather the angle which they are using there is A. So let's put in A. So this means that what we have is 2 tan A multiplied by 1 over sec squared A, like that. That is what we have. And that will end up being 2 tan of A multiplied by cos squared of A. And this is easy. We know what tan is. Tan is always sine over cos. So tan of A will be sine of A divided by cos of A. And then our sine, our cos there will be squared. So it's cos A multiplied by cos A. That is how we get the squared. And if you look carefully, the cosines, they end up cancelling. And what we end up having is 2 sine A multiplied by cos of A. And this is sine of 2A. And this by now you should easily be able to see that what we have here is a double angle identity. So indeed, the right hand side and the left hand side are equal, because that double angle identity is just sine of 2A. So as you can see, therefore, our sine of 2A is indeed equal to sine of 2A. So we're done with that problem. I hope it does make sense. Just give it some thought. Now let's have a look at the second one. We are still required to use double angle identities to prove this. For this one, what we have is cos of 2A equals 1 minus tan squared A, all divided by 1 plus tan squared A. This is what we have. So let's zoom in and see if we can take the right hand side and somehow make it to amount to the left hand side. What is very important for us to quickly realize is that that denominator there is simply sec squared A. That's the first thing we are supposed to realize. So which means we have 1 minus tan squared A, and this is just multiplied by 1 over sec squared A. And on the previous page, we established that 1 over sec squared of an angle gives us cos squared of that angle. So what that means is that we'll end up having 1 minus tan squared A multiplied by cos squared A. And tan, we know what it is. It is just sine squared A divided by cos squared A, and this is multiplied by cos squared of A. And all what we need to do here is to just do some grade 9 foiling. So you just multiply through, which if you look carefully, you'll get cos squared A, and then minus, you will see that the cos's will actually cancel. You will get sine squared of A, like this. And this will obviously be the double angle, what you would call it, identity, because this you can write as cos of A, because it is squared, multiplied by cos of A minus sine of A multiplied by sine of A. And if you look carefully, this looks like the cos identity when you have A plus A. And if you look carefully, this becomes cos of 2A, which is what we had on the left hand side. So we can now conclude and say we do indeed agree that cos of 2A is equal to cos of 2A. It is that easy. So the important takeaway is that you should make sure that you are able to manipulate trigonometric expressions and be able to use all the identities which we learned in order for you to be able to get to answers like this. You just play your way around, you do the manipulation, and I promise you, you will definitely get the answer. So let's have a look at this one, where we have tan 2A equals 2 tan of A divided by 1 minus tan squared of A. If you look carefully, by now you should know that tan is obviously equal to sine of the same angle 2A divided by cos of the same angle 2A. So these we already have. So I might as well just use our previous work. We already have them. So if you look carefully, I'll just copy that sign there, which we proved that it is indeed true. And then I'll fetch also the cos and just divide the two. And there you go. That is just going to be what our answer is. So sometimes we don't need to work hard. We just need to work smart. So I'm going to have sine, which is 2 tan A divided by 1 plus tan squared A. Then we are dividing by cos, which I'm just going to multiply by 1 over cos, which is going to be 1 plus tan squared A divided by 1 minus tan squared A. So that was 1 plus. So this and that cancel. And as you can see, our answer tan 2A is equal to 2 tan A divided by 1 minus tan squared A. That is how we prove that identity. Let's now have a look at example 12, where you are required to express sine theta all to the power of 4 multiplied by cos theta all to the power of 2 in terms of cosine, of cosines, of multiples of theta. So what we already know is what we have worked out before. So already the sine theta to the power of 4, in a previous working, we did work it out and we found it to be this here. So what I suggest, in case you are confused, is that what you should do rather is rewind the video to see how we obtained that. And then also what I'm going to do is quickly write down the expression for cos of theta, not as a double angle or a square power rather, but as a double angle. So it will be 2 cos of 2 theta. This is what I have. So essentially, what we have when I look at these two, when I look at sine for theta multiplied by cos squared theta, I'm just multiplying these two expressions which I found previously, which will be the 3 over 8 minus 1 over 2, and then plus 1 over 8. And this is getting multiplied by what we have as our cos squared theta, which we have showed, or we did take time before to prove what it is. So this will be plus 1 of cos 2 theta, like this. So now all what I need to do is to multiply these. So what I'm going to do, multiply by the half. I am going to end up having 3 over 16, and then minus 1 over 4 cos of 2 theta plus 1 over 16 cos of 4 theta. Then I carry on multiplying. And so what I did was, now I was just multiplying these terms in. That is how we got this blue one. So now I'm just going to multiply the purple stuff there. So if you look carefully, we'll multiply half of the cos 2 theta, which will give us 3 over 16 cos of 2 theta, and then minus 1 over 4. The cos 2 theta and the cos 2 theta will multiply to give us a squared, and then plus, this will be 1 over 16. Then if you look carefully, we'll have cos of 4 theta multiplied by cos of 2 theta. So we have a couple of problems here. This one here is a problem. But how are we going to solve that problem? How we are going to solve it is by realizing that this is a double angle. So it's just going to be cos squared 2 theta. My apologies, it's not theta, but rather 2 theta. So that will just be 1 over 2 into 1 plus cos, double the angle, it will be 4 theta. That is how we are going to solve that one. Let's just change it. So that's minus 1. And then we just now need to go and deal with the other portion, this side. And what I'm going to use here is, there's an expression that we wrote some other time, which was that if you have cos of A multiplied by cos of B, this becomes half of cos of A plus B, and then plus cos of A minus B, like that. So we had an expression which was like this. Okay, so that's what I'm going to use to expand that. So I'll quickly do its expansion, and you need to make sure that you remember this here. So that is why we had to quickly write down these earlier at the beginning of this session. So let's go and use it now. So we have cos of 4 theta multiplied by cos of 2 theta. So this means we'll have half of cos of 4 theta plus 2 theta plus cos of 4 theta minus 2 theta, like that. So this cos of 4 theta cos 2 theta will simply be half of cos of 6 theta plus half of cos of 2 theta. So I can go and put those there. So what does this mean? It means that my answer, sine 4 theta cos squared theta, will be equal to the first part, which I will just copy as it is, like that. And then the second part will be plus 3 over 16. That doesn't change. Cos of 2 theta minus 1 over 4. Very important, that part there which is multiplied by minus 1 over 4, it changes. It becomes 1 over 2 into 1 plus cos of 4 theta. And then plus 1 over 16. So what multiplies the 1 over 16 is what we have above here, 1 over 2 cos of 6 theta plus 1 over 2 cos of 2 theta. So we can go ahead and finalize this and add some like terms here, which will end up giving us, let's see, so there's the constant terms. So when we add the constant terms, you'll see that what we have is 6 or 3 over 16 minus 1 over 8, which can be written as 2 over 16, which will give us 1 over 16. And then if we look at the terms which have cos 2t, you have 1 here, which is 1 over 4, which can be written as 4 over 16, and then plus this one here, which is 3, so that would be negative 1 over 16, and then plus this one here, which is 1 over 32. So that can be written as what? 1 over 32 minus 1 over 16, which is 1 over 32 minus 2 over 16 minus 2 over 32, which will just be, sorry, yes, this was 1 over 16, that's correct. So the other one will be negative 1 over 32. And we will have cos of 2 theta. And then we have a 4 theta, which, where is it? Let me think carefully. Let's quickly rectify this. Let's look at the two cos 2 theta terms. So this here will be negative 4 over 16. This here is 3 over 16, so we're left with negative 1 over 16. Then plus this term, which is 1 over 32. So that will give us negative 2 over 32 plus 1 over 32. So that becomes indeed negative 1 over 32 cos of 2 theta. Then let's look at the 4 theta terms, which is one of them. It's this one, so it's negative 1 over 8, and it will be added to 1 over 16. So this will be 1 over 16 minus 2 over 16, which will just be minus 1 over 16. That will be cos of 4 theta. And then the last one will be the 6th one, which will just be plus 1 over 32 cos of 6 theta. So this is what our final answer amounts to. I hope this does make sense. This is the answer for sine to the power of 4 cos to the power of 2. Then what we are going to cover next is general solutions. That is our next topic, which we are going to cover. We'll look at general solution problems and see when you are given a problem and they say find the general solution, how exactly do you deal with that problem? So we'll do about 7 examples of general solution problems. Then you'll be in a comfortable position to deal with a lot of trigonometry problems. As the first example for general solutions, we'll look at example 13, which is a continuation of the work which we have done. The question reads, find the general solution of the equation below, and that equation is cos of 4x equals sine of 2x. So this is a very interesting equation because since we don't see any number here, it means we have a 1, and it means also here we also have a 1. So whenever you see such problems where you just have the trig ratios, especially sine and cos, and there's just a 1 or the same number, not even 1, but there's the same number either side, what we are going to do is we are going to use co-ratios. We can't divide them to get tan for simple reasons. The angles are different. That is very important for you to make sure that you note, which is that the angles are different. So we can't go and just divide and say this is going to amount to tan. But what is it which I'm supposed to remember? What I'm supposed to remember is that if I have cos of theta, this I can write as sine of pi over 2 if I'm working in radians minus theta. Or if I have sine of theta, I can write this in terms of cos and have pi over 2 minus theta. Okay. So what I'm going to do is I'm going to convert the sine to a cos, because once the trig ratios are the same, the angles inside are going to be the same. So what I'm going to do is I'm going to say sine of 2x can be written as, if we want to write it in terms of cos, we need to do pi over 2 minus 2x. So what does this mean? It means that our cos of 4x is now equal to cos of pi over 2 minus 2x. And once you have this situation, you should know that the angles must be equal. So this angle and that angle, because you have coses, they must be equal. So what we are going to have is 4x equaling pi over 2 minus 2x. But something which you need to remember that cos and sine are periodic after every 2 pi interval, essentially 360. This we are going to write 2 pi k. Other people who usually like using degrees, this you should be familiar with as k 360 degrees. Then we transpose such that we get 6x equals pi over 2, and this will be plus 2 pi k. Okay, so let's make some space, start dividing and finish this up. So let's finish this up. So you will see that your x will be, when you divide by 6, you'll get pi over 12. And then plus, if you look carefully, when you divide by 6 there, the 2's will cancel. So you'll be left with pi over 3 multiplied by k, where k is an integer. So that is essentially your answer. So this would be an integer. But what you need to remember very importantly is that when we are working with cos, our angle can actually be plus or minus, and it will still give us the same thing. So we can go here and put in plus or minus. For cos, you still get exactly the same answer, but we can leave that out for now and leave this as our half-baked solution. So there's many other problems which we are going to work on. Let us pause on this one and dive afterwards on example number 13. Sorry, example 14.